to emphasize not just glycolysis, but emphasize glycolysis and diminish gluconeogenesis in the glycolysis direction, and also emphasize gluconeogenesis and diminish glycolysis in the gluconeogenesis direction. And we can imagine the points of control, right, are probably in the gluconeogenesis direction at the same reaction points as they are with glycolysis. So let's get a little bit familiar with this. So ATP and AMP are, like with PFK, affect the corresponding step in gluconeogenesis, right? So if we think that in glycolysis, ATP is inhibiting, and AMP is activating. Then in the gluconeogenesis direction, they have the similar but reciprocal effects, right? So in gluconeogenesis, on fructose 1,6-bisphosphatase, right? The enzyme that does the reverse chemistry in gluconeogenesis. So if you need to make energy, right, if you're low on energy, that means AMP is being produced, which means gluconeogenesis, the generation of ATP, the generation of glucose needs to be diminished, and ATP actually has, it's not so much it has a activation effect as it has a subsequent diminishment of the inhibit, so it inhibits the inhibitor of AMP. So it's not as a direct interaction. And that's what the next point was. That's right. Citrate, we also mentioned, so we mentioned citrate in the context of pyruvate kinase. Citrate increase is a signal that the citric acid cycle is churning through a lot of carbon, because as we're going to start introducing later on today, citric acid cycle is that first component that's made. So citrate's being made, that's energy producing, that's ATP producing, and so if ATP is being produced, citrate, that means energy is plentiful, citrate inhibits PFK, the glycolysis enzyme, and it overcomes the, so it inhibits ATP, and citrate inhibits phosphofructokinase. If ATP is plentiful, then AMP is low, and AMP inhibits the gluconeogenesis enzyme, causing gluconeogenesis to go forward. So if we kind of just expand this out and look at these different enzymes, again, notice how one molecule can affect two enzymes oppositely. So that one signal can be read in both a activating and inhibition of, so activates in one direction, correspondingly inhibits the other direction, which means it favors one direction in two different ways, right? So glycolysis, AMP, good. Gluconeogenesis, AMP correspondingly down, right? 2,6-bisphosphate, right? We said 2,6 is an activator, so it correspondingly inactivates gluconeogenesis, right? ATP, citrate, inhibit. Look at the pyruvate kinase and then the two steps that bypass pyruvate kinase, right? 1,6 activates. ATP inhibits. Here, the signal, it's ADP, but ADP inhibits in the opposite direction. So high ATP means high AMP, activating in that direction, decreases the inhibition, and produces ADP, which inhibits in that direction, all of which are different ways of the same phenomenon, ATP needs to be made, in regulating this process to maximize the making of ATP. And then in the reverse direction, right, so acetyl-CoA, so we said that citrate being made is an indicator of high levels of citric acid cycle going on. It's made from acetyl-CoA, and acetyl-CoA is the product of fatty acid metabolism. So if there's a lot of acetyl-CoA, that means the citric acid cycle is functioning, and there's a lot of energetic material going into that. So acetyl-CoA can stimulate some of that being converted back into glucose, right? So there's a lot of switches on and off here, but if we look at it in a global sense, just think, ultimately, these are a lot of reactions that have a goal. They're being used for a purpose, right? The purpose can be either consuming glucose to make energy, or preserving glucose if there's enough energy. And I think if you look at it that way, then we can start to see relatively easily what the patterns are and how these regulation events are complementary. Now in the liver, we're going to focus on this in a little bit more detail because the liver is where the 2,6-bisphosphate is made. And just as with any of the other regulatory steps, we'd say, think about, as an example, fermentation, right? Why do organisms undergo fermentation, undergo anaerobic glycolysis? What's the fundamental point of that we talked about? NAD, right? In glycolysis, two NADs are converted to two NADHs, which, if there's no oxidative glycolysis going on at all,